So today let's go ahead and take a look at piecewise functions. We're going to be understanding and interpreting the graphs and the situations that are described by these piecewise functions. So without much ado, let's go ahead and get started. So right off the bat, we have this scenario introduced to us about parking lot and the parking fees. So we have three different scenarios: a flat rate of $5 for any amount of time up to and including the first hour, a flat rate of $12.5 for any amount of time over 1 hour and up to including 2 hours, a flat rate of $13 plus 3 per hour for each hour after 2 hours. So right here we can see that we have these three amount of time, and that's gonna charge us three different prices. So let's go ahead and get to example one, which is basically a question about our example. So let's move this. Using a graphical model, let's represent the function of the parking fees. So how do we get a graphical model? So we want to get some key points down. So let's drag this on the right so we can have some math. Okay, let's go ahead and have some key points. So we would want to have let's have parking time in hours, and on the right we will have parking fees in dollars. Okay, this sounds about right. And let's do it. So at 0 hours, we will obviously be paying none. At 15 minutes, let's say how about at 30 minutes? How much will we be paying? We'll be paying $5 because it's with up to and including the first hour. So we'll be paying $5. How about 1 hour? So up to and including the first hour, we're still paying $5. And then let's talk about how about we do an hour and 30 minutes. How much are we paying now? So we no longer qualify for the first bracket. We're going to go into the second bracket. So a flat rate of $12.5 for any amount of time over 1 hour and up to including 2 hours. So 1.5, obviously that qualifies for the second bracket, so it's 12.5. Let's see 2. What is 2 hours gonna do? So for a flat rate of $12.5 for any amount of time over 1 hour and up to and including 2 hours. So it means that at 2 hours it's still included in the second bracket, so it's still $12.5. So let's see how about 2.5. Let's see what 2 hours and 30 minutes is going to cost us. So a flat rate of $13 plus 3 per hour. So we already parked for 2 hours, which is 13. We got the flat rate and 3 per hour, but we only parked for half. So we have to do 3 times a half, which is 1.5. So 13 plus 1.5 will get 14.5. How about 3 hours? So 3 hours, we will have a flat rate of 13, and for every hour parked after 2 hours. So we parked for 1 hour after 2 hours because 3 minus 2 goes to 1. So 1 times 3 plus 13 is going to be 16. And then 3.5 would just basically do 16 plus 1.5, so 17.5. And then 4 hours, it's going to be 13 plus 2 times 3, which is 19. Right? So we have this table of values, and right after, now you should be able to go ahead and graph this on your own, which I'll give you a few seconds to do. Okay, I hope you have graphed it on your own, but I have also got us a proper table here that has the values. So this is our ghetto version of the values, but now we have an official version. We have a better version. So we should be able to graph this, and after that we should have a graph. So let's go ahead and interpret the graph. So I also plotted my own graph right here. So this is my graph. Looks pretty good, pretty clean. So we can see right off the bat, we can see 3 different brackets. So right here, 1 bracket, 2 bracket, and 3 different brackets. Okay, that seems pretty clear. So let's interpret this graph. So we plotted the points from the table of the values. We use solid dots to include a value, and we use an open dot to exclude a value. So there's a solid dot at 0, 0, and an open dot at 0, 5 because the parking fee at 0 hours is $0. And we can't have 2 points. We can't have 2 y values for the same x, or else this isn't a function anymore. This is a relation. There's a closed dot at 1, 5, and an open dot at 1, 12.5 because the parking fee at 1 hour is $5, and vice versa for 2 hours. And the last part that is the only really interesting part about this is that the last part of this graph continues in a straight line because the rate of change is constant after 2 hours. Before that, it's not the rate of change. The function itself is constant. Let's talk about the domain. So what can we interpret about the domain? So the domain of this piecewise function is x is greater or equal to 0. And the function is linear over the domain, but it is discontinuous at x equals to 0 or 1 and 2. So we want to talk about something about discontinuity. So continuity is something that we're going to be introducing right now, and we're going to slowly be talking more and more and more about it. Eventually, even in calculus, it's a huge concept. So continuity, what is continuity? So we can talk about if a function is continuous or not. So if a function is continuous, the very simple explanation is that you can draw the entire function without having to lift your pencil. So what function is continuous? Well, a quadratic function is obviously continuous. You could draw that without lifting your pencil. A square root function is continuous. A cubic function is continuous. Any of these functions are all continuous because you can draw them without lifting your pencil. But this function right here, when we have a piecewise, this is not continuous. Obviously not. When we have this, we have to lift our pencil to draw that segment, lift our pencil to draw that segment, and finally lift our pencil again to draw that segment. We have to lift our pencil 4 times to draw this function. This is not continuous. So what other functions are actually not continuous? Well, we have this, right? We introduced rational functions. They're discontinuous because you have to lift your pencil to draw this part and then draw that part. Right? And then eventually we're going to see rational function like this. Right? We'll have to lift our pencil 3 whole times, and we're going to have asymptotes. And this is perfect science of discontinuity. Right? Anyways, so this is a really simple explanation of continuity. Is that when you have to lift your pencil to draw a function, it is discontinuous. Let's go ahead and introduce ourselves the actual formal definition of a piecewise function. So what is a piecewise function? What is a piecewise function? Well, a piecewise function a piecewise function is a function defined by using two or more rules on 2 or more intervals. And as a result, the graph is made up of 2 or more pieces of similar or different functions. So we're gonna see this. This may seem really broad to you right now, but right as we're gonna go ahead and do 2, and then this will clear things up for you hopefully. Let's go ahead and do example 2. So we're gonna use algebraic model to represent the function for parking fees. Okay. So as we talked about previously, we could divide this thing into 3 different parts, but we also have to include this part at the bottom. We already have the graph, right? We already have the graph. This is gonna save us some time because we have the graph. So the graph is obviously divided into 4 parts. We'll have 0, 0. We have this little constant here, and we'll have this little constant here, and then we'll have a variable here. We'll have a linear here. So let's see. Obviously, we could define this as why is this upside down? So okay, this is unsatisfying. So at x equals to 0, we'll have x equal to 0. So function 1, function slash point 1. X equal to 0, y is equal to 0. Or we could define it formally. Y is equal to 0 if or when x is equal to 0. Let's talk about function 2. So we're talking about this little constant part here. So function 2. So y is equal to 5 if slash when. Now, we actually have to define this. It's no longer when x is equal to a certain value. It's an interval. So if 0 is less than x, is less or equal to 1. Right? Does this make sense? It's less than x, less than 0, and strictly less than 0. It's not less or equal to because we already defined 0. But it is less or equal to 1 because it says, where's the question? Where did the question go? What? Okay, that's interesting. We lost the question. Well, anyways, the question says, including and up to a flat rate of $12.5 for any amount of time over 1 hour and up to including 2 hours. And for the first one, it's a flat rate of $5 for any amount of time up to and including the first hour. So it includes the first hour in there. So I'm going to finish this. So function 3. we're now looking to finish this little constant part. So function 3, where y is equal to 12.5, if slash when 1 is less than x, is s or equal to 2. Right? Makes sense. Makes sense. And then finally, we'll have part 3, where we have this linear part, which is really the only interesting part about this entire thing. Is that function 4. This is pretty much the only part. So why we will actually have a function instead of having a constant. Instead of being constant, it will actually be a function. It will be a linear function. So 13x, because 13 plus 3x. We pay a flat rate of 13, and for every extra hour, we will have to pay $3 extra. So let's also define this: if slash when x is greater than 2. Right? This is a strict. So let's see. When you're getting assessed on this, so when you do this on a test or a quiz or any sort of assessment for marks, you're gonna have to write all of this out. But instead of writing if and when or whatever, you're gonna have to actually define a function f of x. So we'll combine all of these 4 different things that we wrote into one big function, which is right here. This is our function. F of x is equal to 0 if x equal to 0. It's equal to 5 if 0 is lesser than x, is lesser or equal to 1. And all of this makes sense. So let's put this right next to our graph. Perfect. So now let's interpret this a little bit. Let's go ahead and talk about it a little bit. So the domain of this was clear. It's x is greater than 0. And the function is discontinuous at 0, 1, and 2 because there's a break in the function at these points. And overall, our function that we define, our algebraic function, does seem to match up with our graph. And it looks like we have done a pretty good job. Let's go ahead and do example 3. So example 3 is completely brand new. It has nothing to do with whatever that we just talked about. This example. Let's talk about example 3. So representing a piecewise function using a graph. So this time we got the function. Last time we didn't have anything, but last time we got pretty good. So this time we have the function and we just need to graph it. So let's look at this. So whenever you are given a piecewise function, you want to look at the connecting point. So from the equations given, you can see that the graph consists of part of a parabola because we have x squared and we have a line. And we want to see where is this connecting. So both of the function that we have, it includes 2, right? Since this is where the description of the function changes. So as when we see if x is equal to 2, on the left of x equals to 2, we're going to have a parabola, and on the right of it, we're going to have a line. So this is where the description changes. So let's go ahead and create a table of value. So f of x is equal to x squared. So let's see, let's get some values. So let's say 2, 4 is a value. 1, 1 is a value. So we only want to get values less than 2 because this is where it's defined. We don't want to get any values more than 2 for x squared because it's not defined when x is greater than 2. So 1, 1, 0, 0, negative 1, 1, and negative 2, 4. And then we'll have our second function being a linear function, f of x equals to 2x plus 3. So now we want to start on 2 but instead of going to the negatives, we want to go to the very positive. We're going to go up. So we'll have 2, 6, 2, 9, 2, 7. What am I doing? 3, 9, 4, 11, 5, 13, and 6, 15. So we have all of these. And then you should be with these points, you should be able to go ahead and graph it, and you should be able to connect these dots so to have a general shape. So I'll give you a few seconds to connect it. And meanwhile, I'll also bring in our table of value right here. So this is a better version of our whatever we had. So this is our table of value. So you can see we have 2 functions. Now you should be graphing it, hopefully by decimals or by hand. Okay, I hope you're done, and I want to go ahead and give you my graph. So this is my graph. So as we predicted, at x equals to 2, this is where the description of the function completely changes. So we'll have a parabola on the left, we'll have a line on the right. But notice, instead of having some points like this right here, it's just lines. Now we have a parabola, and we can include any function really in here. So let's analyze this a little bit. So we have a solid dot placed at 2, 7. Since x equals to 2 is included with f of x equals to 2x plus 3. And an open dot is placed at 2, 4, since x equals to 2 is not included in f of x equals to x squared. But because we have this huge jump right here, and we can't really draw this without lifting our pencil, right? So because we have this huge jump, this function is discontinuous. Okay, it's pretty simple. Let's go ahead and get to example 4. Where is example 4? So example 4. Represent a piecewise function using an algebraic model. So this time, instead of having the algebraic or whatever, instead of having this thing, we have a graph. We have to interpret the graph. So let's see, how many different functions can we really tell from this graph? Well, right here, off the bat, I see this part, this whole part of everything x less than 2. This is clearly a irrational function. It's 1 over x, obviously. We have the key point of -1 and -1 and 1, 1. This is clearly 1 over x. And then we see this odd line right here, and it's discontinuous over here, which is not a characteristic of a 1 over x, right? This is an odd line. This is a constant function for everything greater than 2. Let's go ahead and write this down. Now, this is pretty easy. So the one piece is the reciprocal function. So we will have let me write actually. So we'll have y is equal to wow, why am I not able to write? Y is equal to 1 over x when x is less than 2. X is less than 2. Now, you want a question. Is this less than, or is this less than and equal to? Because we have this solid dot at 2 for 1 over x, it's included. So no. And this is correct. And now, since we have our first part done, let's go ahead and look at our second part. So y is equal to what? So this is a constant function that was already defined. So 1 equals to 2. And now, x is greater. Is this greater or equal to? Right? It's greater because we have an open dot. So this is wrong. And this is correct. So we have to find our function. So let's see. The solid dot, we'll have a solid dot indicates that point 2.5 belongs within the reciprocal function. So when we have a formal answer, we wanna write something like this. Right here. This should be your final answer. You should define a function f of x. It's equal to 1 over x if x is less or equal to 2. 2 if x is greater than 2. So it matches what we did here. Perfect. Let's go ahead and get to the very, very last one, where we have to talk about some continuity problems. So reasoning about the continuity of a piecewise function. When we look at this thing, is this function continuous at the point where it is pieced together? So this function, instead of this question, interesting. Instead of asking you if the function itself, usually before we have done this, before we looked at individual functions, we always look at the function, let's say x plus 1, or so let's say x squared, so something like x squared, right? You will look at this, or x plus 1, something like that. You will always look at these individual functions and be like, okay, are they continuous or not? But instead of doing that anymore, we're going to look at if they're pieced together correctly. So let's see. How do we do this? This should be very, very easily done. So let's go ahead and see. The function is continuous at the points where it is pieced together if the function being joined have the same values at these points. So let's say at x equals to 0. So actually, let's just do an example. This is so much easier. So let's calculate the values of the function at x equal to 0 using relevant equation. So obviously the relevant equation is the first one, where x is equal to x plus 1, and then 2x plus 1. Let's go ahead and plug 0 into there. Let's plug 0 into the first one. We'll have g of 0. So we'll have x plus 1. G of x is equal to x plus 1. But g of 0 is going to go ahead and equal to 1. Because we'll have 0 plus 1, right? That makes sense. Okay, fine. And then here, we will have g of x is equal to 2x plus 1. So let's also input 0 in there. So 0 times 2 plus 1. Okay, still 1. Okay, good. Perfect. Because the two values are the same, so the linear pieces join each other at x equals 0. Joins. So when we have a graph like this, So let's say x plus 1. So, okay, actually, I'll give you the graph later. But either way, we have 0 included in this, so it's included in x plus 1, so it's a closed dot. But then we'll have an open dot for the second function, 2x plus 1, at the same place. But because it's already a solid dot, we can no longer open dot it. It doesn't work anymore. So that part is defined, and we are joined together. So let's go ahead and check the second part. So 2x plus 1. So where's the second joining part? It's x equal to 3. So g of x is equal to 2x plus 1. And then we want to see at what happens at x equals to 3. So we'll have 6 plus 1, 7. And then let's see this part. G of x is equal to 4 minus, 4 minus x squared. So x squared, so 3 squared, so g of 3. We'll have 3 squared, which is equal to 9. So 4 minus 9 is negative 5. These y values doesn't equal to each other. So the two y values are different. So the second linear pieces does not join with the parabola at x equals to 3. So the function overall is discontinuous. So is the function continuous? So no, it is not. It is discontinuous since there is a break in the graph at x equals to 3. You can go ahead and verify this by graphing using a graphing calculator or a Desmos. And the homework today from me, the bonus extra homework, is to find out how to actually graph a piecewise function on Desmos, because Desmos is going to be your best friend. So right here we have the graph. So we can see, okay, we can clearly see 3 parts. So this rate of change right here is kind of normal, and this rate of change is getting much steeper. And finally, we have this huge break right here, and then we have this kind of little parabola on the very bottom. So we went through some examples of piecewise functions. Let's go ahead and summarize this entire class up. Let's go ahead and look at in summary. Let's look at some key ideas, and let's see what we need to know from this little lesson that that might be getting assessments on. Okay, wow, that's really big. So key ideas. Some functions are represented by 2 or more pieces. These functions are called piecewise function. Each piece of a piecewise function is defined for a specific interval in the domain of the function. So what do we need to know? So to graph a piecewise function, we must graph each piece of the function over the given interval first. And the piecewise function can be either continuous or not. If all the pieces of the function join together perfectly at the endpoints of each given intervals, then the function is continuous. Otherwise, it is discontinuous at these values of the domain. And with that said, our lesson is done, and there is homework for you on page, on page 51, 52, 53. There's about 15, 16 questions, something like that. I suggest you doing all the odd numbers or all the even numbers to get your practice in. And with that said, have a nice day, guys.